Okay, welcome back. So today we're going to talk about our final topic for review for AP exams. We're going to talk about today a mini review of oxidation and reduction chemistry, specifically called redox, and we're going to blend in with it some issues of spontaneity and equilibrium. I know it's a kind of a stretch to bring those three together, but we'll find here at the end that they all come together. So I'm going to go through these notes quickly. This is designed as an intro video. This will be followed by one or two videos where I'm simply going through sample AP problems and applying these concepts here. So it's recommended that you watch this video first before watching those others. Okay, so here we go. Just some reminders. Reduction is defined as the gain of one or more electrons, and oxidation is, of course, the loss of one more electrons. Remember that one cannot exist without the other. It is possible to ionize substances outside of solution. So, I mean, I guess you could say that one could happen without the other. That is the loss or gain. But when we use the phrase reduction and oxidation, we mean it to say we say it to mean that they occur simultaneously. One happens along with the other. And also, when we have to balance these things, we will apply the law of conservation of mass, of course. I bring that up because oftentimes we forget that we have to balance charge as well. Electrons do have mass, so we must balance them as well. So, in a general sense, atoms have a tendency to pull electrons towards them. When it's part of a bond, we can call this electronegativity. We can even call it electronegativity, I suppose, if that helps us. But all we really need to understand is they have a tendency to pull electrons toward them to fill up a valence shell. Some of them have a stronger tendency than others, and we can measure this tendency against a defined reference point, just like any measurement. And that defined reference point is called a standard hydrogen electrode. It is our defined zero value in this system, and we measure, or the unit we use for this is voltage, which stands for electrical potential. So these tendencies are measured against this electrode, and they're called standard reduction potentials. Just remember, the word standard applies to standard states, and these are the defined conditions, or defined standard states. 1 atm, 1 molar, 298 K, and in biochem applications you typically bring in pH. We won't see that, but just in case, it's a pH of 7. So this is a little reminder for me to show you a chart. So what you're seeing on the screen is excuse me, the constants that are given in an AP exam. This is an actual picture of that sheet. Notice the title is Standard Reduction Potentials, and they're all listed, and they have a voltage listed in this column. Please understand that they're all written as reductions. So you'll be referring to this table on any redox question. So again, I wanted to remind you, these are all written as reductions. They are shown with electrons being gained. The higher up the list that substance is, the more likely it is to take electrons from an ion or metal below it, over here on this side. So the higher on this side will take from things lower on the product side. Okay? So just keep that handy. We'll refer to that frequently. So we'll continue. You see the number listed, that was the voltage, to measure over its tendency. The higher that number, we will find that the more likely something is to occur. And it's going to be a linking concept in a few minutes. So we can see that the reaction here shows that copper ions react with lead to produce pure copper and lead 2 ions. Now if we go through and assign oxidation numbers, we see that copper went from a positive oxidation state of 2 to neutrals, or 0 oxidation state, and the lead went from 0 to positive 2. So copper's oxidation state decreased, indicating reduction. Lead's increased, indicating oxidation, making copper the oxidizing agent and lead the reducing agent. Now when we balance this, remember, we have to separate into 2 half reactions. So I've written this one as a reduction. I wrote copper to copper 2+. There were no oxygens, were no hydrogens. I balanced the charge with electrons. Same process over here for lead. Now, the number you're seeing here is me looking at the standard reduction potential table. Let me be clear. You'll find this reaction on that table because it is a reduction. So I simply copied this directly from that table. Please refer to it if you need to. And over here, I've written the reduction potential from the table. This is the standard reduction potential for the reverse of what's indicated. It's the reduction reaction I'm showing. So I wrote as a reduction. Now, the reason I'm doing this is because in a moment, you can see the formula here, when we calculate the potential of this particular cell, we in the formula we include this negative sign. Well, that negative sign does the job of switching this sign for us, so there's no need for us to switch it here. Now, if you did choose to switch it here, please don't apply this negative sign here. That would cause an error. So plugging in the values from the table, we see that this cell, as written, has a standard reduction potential of 0.28 volts. Now, the fact that that cell potential is positive means it's spontaneous. Now, we're going to get to why that is in just a moment. Before we do, I wanted to refer you to this drawing here, because you are required to do this drawing. So some issues I just want to point out. The oxidation part occurs at the anode. So remember, lead is oxidized, so I'll just put the oxidation step. Reduction occurs at the cathode. If you ever forget that, remember oxidation and anode begin with a vowel. Now, in each half reaction, there is a neutral metal. You can see lead here and copper here, so the electrode in that cell is listed with that metal. In the solution is the other part of that half reaction. So in the lead cell, we see there's lead 2 ions in solution, and there's usually a neutral or another ion present to neutralize the other ion that's involved in the reaction. And typically they're generic. They don't react in the conditions that we have here. So nitrate's a good example. Sulfate is commonly used. Just understand that there's a counterbalance ion there. In the other cell, you see the copper on the electrode, the copper ions, and again the counterbalance. In a voltaic cell, which this is, where the potential is positive, the electrons will move from the negative electrode to the positive. That's actually true in all cases, but in a voltaic cell like this, the electrons go from the anode, because that's oxidation, they're losing electrons, and will go to the cathode, the positive electrode. Okay. At the top we see a voltmeter symbol indicating the potential, and the last piece to the puzzle is this little bridge here. This is that salt bridge we discussed in class. It is necessary to allow a balance of charge to exist, otherwise the charge balance would become tremendous. For example, you can see in this electrode, the electrons are leaving. Well, as they leave, we are depositing more lead 2 ions in solution, leaving the nitrates unaffected. That is a buildup of positive charge. So this salt bridge functions in that it provides ions that will migrate to counterbalance that buildup. So the negatives will always move towards the oxidation electrode, the anode, and the positives, for the same reasoning, will go to this side, because as the electrons build up, we're pulling the copper ions out of solution, creating an excess of negatives, so we have to balance them with the positives. So that's a voltaic cell. That's how you draw it. Now, back to the question. We said that when E for the cell, or the standard reduction potential for the cell, is positive, it's spontaneous. But why? Well, here's the relationship which indicates that. It turns out that delta G, which we learned previously was our determining factor in spontaneity, remember delta G is related to the entropy change in the universe. However, delta G is different in that it applies only to the system. So it's a simplified way of determining spontaneity for a system. And remember, we learned that when delta G is negative, the reaction is spontaneous. Well, if this relationship is true, and these two values are constants, you can see them defined here, where n is the number of electrons transferred, F is Faraday's constant, a positive number, and you can see its value here. If n and F are both positive, and delta G must be negative for spontaneity, then that tells us that when when E is positive, it is spontaneous. So there's our definition of why a positive cell potential represents spontaneity. Now remember, that means that the electrons will go through this cell until there is no more driving force. Now, typically, that is when delta G becomes 0. We reach an equilibrium state, a balance state. That does not necessarily mean it goes to completion. It's until the reaction has established a delta G of 0, which we define as equilibrium. So that's going to come back. The issue is going to come back in a few minutes. So, what happens though if these are not at standard states? You see the degree symbol. Remember, that means standard states. Well, it turns out that relationship still holds true, and at non-standard states, it's the same exact thing, except of course because it's not at standard states, we don't write E with the degree symbol. It is the potential of the cell at not standard states. The most common way that standard states are adjusted in this test will be with concentrations. So they will no longer be at 1 molar. It's not a temperature issue. As a matter of fact, it has to be concentrations. You're not given anything else to work with. So let's continue. And now this is some new material for this year. So I just wanted to make sure you got this. I didn't want to sneak it up on you too much. Delta G gives free energy change at non-standard states, can also be determined at non-standard states. Obviously, that's why the degree symbol is missing. And here's the formula for doing so. This formula appears at the end of chapter 19 in our text. It's a section that we missed, or we skipped actually. So I want to make sure you've seen it. This is a very important relationship for redox chemistry and for equilibrium. So there's a possibility for many test questions here on the AP exam. We see that delta G at non-standard states is equal to the Gibbs free energy change at standard states plus a factor, an adjustment factor. Now let's talk about these values. R, capital R, is the gas constant, the joules version, so it's 8.314. T is the temperature in Kelvin, and Q is something we've seen previously. That's the reaction quotient. Remember, the reaction quotient is determined from the law of mass action, just like equilibrium values. It's the products raised to their exponents divided by the reactants raised to their exponents. Solids and liquids do not appear. Remember, the difference between Q and K is that Q is like a temporary condition, and we compare it to K and decide if it will shift or not. Okay, and this is where equilibrium fits in. So, some things to remember. At equilibrium, K is equal to Q, and delta G is equal to 0. That's way back in the equilibrium or spontaneity chapter earlier in the year. And if that's true, if those two things are true, then at equilibrium, delta G at standard states equals this relationship. Now that derivation is shown here. I don't want to get too far ahead. So remember, at equilibrium, delta G is 0. Then I just substitute into that equation at the top, and we rearrange, and we see a method of finding the equilibrium constant for a reaction mixture when we're not at standard states. So that formula is available. This formula here. Let me put a little rectangle around it. That formula is available in the AP's formula guide. It is a method for determining the equilibrium constant from Gibbs free energy. Now remember, Gibbs free energy can be found using the Gibbs free energy equation, delta G equals delta H minus T delta S, or from using the sigma equation. So refer to your notes and or text for those. So, okay, so how does this fit in with oxidation and reduction? We've got all these equations we've introduced. And the key thing is that it allows us to determine the potential, E, at non-standard states. We have a method for doing it at standard states. It's potential of the reduction, or the cathode, minus that of the anode. But how do we calculate spontaneity? How do we calculate E at non-standard states? So remember, we have these definitions from before, and we also have this relationship here that we established a few minutes ago. Now I'm going to do some substitution. I'm going to substitute in place, and here's what it looks like. Let me just display the whole thing, because this is going to be quite a mess, but please repeat it several times if you need to. Here's that relationship for delta G at non-standard states. Okay, we're going to substitute both of these terms in place, so please just kind of follow along. Now I'm going to divide both sides by negative NF to bring E standard states minus RT over NF times log of Q. Now typically this is done, I honestly don't know why, but it's just a relationship between natural log and base 10 log, and so I'm going to apply this relationship. Now you just have to trust me. So from here to here, what you see is the combination of R times T, which is going to be 298, this only applies at 298, divided by F, Faraday's constant, times 2.303, and it rounds to approximately that number, divided by N, the number of electrons transferred, times base 10 log of Q, which is the reaction quotient, the law of mass action. So in this spot is where you would put the concentrations of the products and reactants if they're not at standard states. Okay, that's important that you understand that Q equals products over reactants raised to their exponents according to the law of mass action. That is known as the Nernst equation, and it's useful for determining, again, potential at non-standard states. So with that quick intro, there's a few edit points there. I'm sorry, had a little bit of choppy editing, but watch this video first. The formulas used here will be applied to 2 sample problems in a few moments.